Consider the figure on your screen. This is the transfer characteristic of a limiter circuit. In this region, the limiter acts as a linear circuit. The output is proportional to the input. That is, V0 equals kVi, where k can be greater or lesser than 1. If input Vi exceeds either of the thresholds, L positive or L negative, the output is saturated or limited. Let's pass a sinusoid through this limiter circuit. The solid line is the output and the dotted line is the one that is removed. We also say that these parts get clipped, and therefore the limiter is also known as a clipper. What we have just seen are what are known as hard limiters. Soft limiters also exist with a transfer characteristic like this at the bottom of your screen. They have smoother transitions between linear and saturation regions. In saturation regions, their slope is greater than 0. Look here. Compare this with the straight lines here and here. Both these limiters find uses in applications. So, how do we actually make one? Diodes and resistors can be combined in a variety of ways to make different limiter configurations. Some of these you can see on your screen. The diode model used is constant voltage drop. Piecewise linear model could also be used, which would entail that the slope of the saturation region is greater than 0, which means that this part here will not be a horizontal line, but a straight line with a slope. So let's look at them one by one. The first circuit, number 1, is that of the half-wave rectifier, except that here the output is taken across the diode. For Vi less than 0.5 volts, the diode is cut off, no current flows, and the voltage drop across R is 0. Thus, V0 equals Vi. As Vi exceeds 0.5 volt, the diode turns on, eventually limiting V0 to one diode drop, 0.7 volts. The second circuit is similar to that in the first one, except that the diode is reversed. Double limiting can be implemented by placing two diodes of opposite polarity in parallel, as you can see in the third circuit. Here the linear region of the characteristic is obtained for Vi is lesser than equal to 0.5 and greater than equal to minus 0.5. You may be wondering why 0.7 is written. Remember when we were first studying diodes, 0.5 volts was the point where the current started to increase. You can see here that these circuits are not hard limited but soft limited. Why? Because the transition between 0.5 and 0.7, the point where the diode is conducting, or when the limiter is applied, then that transition is soft or smooth. Coming back to the third circuit, in the range that we just mentioned, both diodes are off and V0 equals Vi, that is the straight line of the graph. As Vi exceeds 0.5 volts, the diode on the left turns on and eventually limits V0 to 0.7 volts. Similarly, as Vi goes more negative than minus 0.5 volts, the diode on the right turns on and eventually limits V0 to minus 0.7 volts. These thresholds can be manipulated. Look at the fourth figure, where a 5 volts battery is used to up the limit. Look at circuit 5. In this circuit, limiting occurs in the positive direction at a voltage of VZ2 plus 0.7 volts, where 0.7 represents the voltage drop across the Zener diode Z1 when it is conducting in the forward direction. For negative inputs, Z1 acts as a Zener while Z2 conducts in the forward direction. Try and work out the graphs for each of these circuits for yourself. This will be good practice.